Okay, so far all we've been discussing are linear predictions between continuous variables, say x1 and x2, at the bivariate, and then now we have multiple predictors. But what happens if we have categorical predictors? Well, I'm going to create a categorical predictor out of x1, and I do that just by, and then I'm going to create another categorical predictor out of x2, make sure I haven't made any mistakes. I checked this code before. And then I'm going to run each one of these and then do a quick summary. So let's get down to the basics here. So the first thing is we have a categorical predictor, which is just a median split. Any value that was, I believe, hold on, let me just see here, greater than the median was assigned 1, and if it was less than it was assigned 0. And so I did that for x1 and x2. And so now we have 3 linear models, and I have a summary for each one. So let's just take a look at what those look like. So the first one gives me a significant predictor, but remember that now we have a binary variable. So C1 is just a categorical variable, and it has 2 values, 0 and 1. So if you put 0 for x at a bivariate level, well, what happens is it doesn't matter what b is, because whatever b is, that is the regression coefficient for C1 as a predictor of y, whatever b is immaterial, because a 0 times anything is 0. So that means that our effect for our 0 group is the intercept. And then the effect that we get when we calculate it for group 1, because there are only 2 groups here, is the incremental effect on top of the intercept. So this is a dummy code. I've created a dummy code, and we're going to talk all about dummy codes and different contrast codes and all of that later on. But I want to show you that in regression you can use these types of codes and for regression as predictors, and then later I'll show you how we can use them as dependent variables as well. But these codes need to be interpreted carefully. So the interpretation of them is going to be different than if we had a continuous relationship. So now we have C1, and then let's take a look at C2. And I think I skipped C2 altogether, didn't I? No, I added, oh, there we go. I added C2 along with it. Now I have 2 significant predictors, C1 and C2. And you'll notice that my multiple R square is now in the 50s for C1 and C2. If I go back up here where I had X1 and X2, notice I'm scrolling all the way up. That would be LM 2.1. Let's do a summary of LM 2.1, and I'll show you what that looks like. We had a much better multiple R square, or adjusted R square. Our adjusted R square was in the 60s. When we take a perfectly good continuous variable and we chop it up, we end up losing variance, and we lose variance in our predictors, but at the same time we lose variance, we lose statistical power as well. And again, this is something that we're going to go over a lot, and what happens when you take a really nice continuous variable and you do something absurd like chop it into little tiny bits. Well, sometimes it helps in interpretation, but it doesn't really help, and it's certainly not testing the effect that we care about. So here I've got 2 predictors, both of them categorical, both of them binary. And what I can also do is expand this into an interaction. I have a non-significant interaction effect, and this is just a demonstration that you can use categorical predictors, but you have to make sure that they're coded in such a way that they make sense in regression. I use dummy coding. Later on we're going to talk about all different types of coding that allows you to compare multiple categorical groups and interpret the effects using regression. Now, the reason why this is important is that you need to see early on that regression can help us test models that were traditionally ANOVA models. So we can take nominal level data and transform that nominal level data into categorical predictors. And those categorical predictors can then be interpreted through a regression model so that you have not just categorical predictors, but then you have numerical results or numeric results that then can be compared and contrasted with multiple different models. That's the advantage of regression. Regression is a flexible general linear model tool, and through this course you're going to learn that regression can do everything that ANOVA can do and more. And this is not a sales pitch to discard ANOVA completely, but I think at this point you need to recognize that regression is a fairly flexible model. Okay, so now from this moment on, what we're going to do is we've got, I believe, 2 more. Do we have? No, we have 3 more videos. So stay tuned for nested data in our next video.